Hello, my name is Marc Fassbender and I'm a PhD student at the University of Ottawa. And I use chemistry, petrology and machine learning to investigate modern ocean settings that potentially host VMS deposits. In this poster, we will explore the systematics of mafic volcanic rocks in modern intraoceanic regimes such as lava basin, and we will compare them to samples from the Archaen Abitibi greenstone belt. First, we created a data compilation of mafic volcanic rocks in submarine environments. This database was then screened for samples that are completely analyzed in titanium, alumina, barium, thorium, zirconium, niobium, lanthanum, yttrium, and ytterbium. And we have chosen those elements based on the significance they have in various lithotechtonic environments, their usage in geochemical discrimination diagrams, their availability in our dataset, and their mostly immobile behavior. This high-quality database contains more than 2,900 samples that were then used to investigate the geochemical systematics. And they range from thermolytic to transoceanic to calculating affinity, and they cover the entire lithotechtonic discrimination diagram. However, samples in these plots significantly overlap, and additional geochemical ratios should be used to identify other potential reasons that might cause these signatures. To overcome this and to better understand the underlying systematics, we use some statistical and machine learning techniques using all 9 elements simultaneously. We have clustered our data using accumulative Rucker clustering, which clusters samples purely on their geochemical signatures without any pre-assigned groups. It starts by assuming that every individual sample forms its own cluster. Then the distances from all other samples are calculated, and 2 samples with the closest distance to each other form the next level of clusters, and so on until every sample is included. In the end, data trees retrieved from which the number of clusters are identified. This resulted in 7 distinct clusters that we have visualized here using principal components analysis. PCA reduces the variables into a limited number of components, and each principal component is affected by all the variables, representing a fraction of the total variance. In our case, 9 elements, hence 9 principal components. The first accounting for most variance, the last for least variance. That being said, this PCA biplot using PC1 and PC2 visualize the most significant geochemical controls in our dataset. Red labels visualize how the various elements are controlled. We can see that there's a transition from enriched to a depleted mantle source along PC1, and a transition from dry melting to fluid flux melting along PC2. To identify these signatures elsewhere, we created a random forest classification scheme that is trained on identifying these 7 target classes elsewhere. The training is an iterative process by which random forest learns what values are meaningful to achieve the best classification outcome and builds a model that can be used as a classifier. We use 80% of our data as a training data set and 20% for validation of blind test data. Our classifier has 500 decision trees, each being trained with 3 randomly selected elements. The predictive results on the blind test data set are illustrated in this table here, yielding pretty good results throughout all classes, as can be seen in this diagonal line here, correctly plotting and identifying 566 of 586 samples, yielding 96% correct classification. We then applied the classifier on some data from the Archaen Abitibi greenstone belt. And this shows similarities of the Blake River group with intraoceanic back arc related regimes such as the northern lava basin. These areas are related to complex microplate mosaics, anomalously high heat flow, rising asthenospheric mantle, and complex spreading regimes. They have a negative, but very weak negative niobium tantalum anomalies, slightly enriched RE pattern, high niobium ytteria ratios, high thorium ytteria ratios as well. So in conclusion, this study shows that accumulative Rucker clustering and PCA can be used to identify a wide range of geochemical signatures. These clusters relate to lithotechtonic environments that can be identified elsewhere using a random forest classifier. And we show that the southern Abitibi greenstone belt hosts geochemical signatures that are largely similar to modern intraoceanic back arc spreading centers like the northeastern lava spreading center that have very weak arc signatures. Thank you very much for your attention.